A river has two basic components. One is external components like its depth, width, cross-section, gradient, velocity, discharge. So which could be mapped, which could be measured, and which could be observed from the outside. And most of the research or understanding on the river system concentrates on measuring these attributes. But behind these, there is some internal relationship actually constitutes the river. What are the internal relationships? Between rock types, soil texture, land use, slope, drainage network, and vegetation. How climate, rainfall, temperature are integrated with geology, topography, lithology, and these together gives rise to vegetation and land use and soil character. And together all these characters lead to the discharge and sediment load. And this discharge and sediment load ultimately guide to develop the morphology dynamics of the river. So this is how a river could be understood holistically. Any change of any of the component among these may give rise to the variation or the changes in the river. Okay? Now, a very simple description of the river system. If it is a small catchment, it is a small reel actually. And this reel catchment has the system composition of numbers of elements. Say convex divide, free face, concave basal slope, deep channels, pockets of say vegetation, and all these elements are interacting together with system behavior and the system relations. Okay, so these are what we identified the system components and their system behavior, source to sink linkage, bank to channel linkage. Okay, and any change in any of the component can give rise to the change in the river as a whole. Now we are in the phase of post-structuralism. Okay, according to this, every river is unique and no two rivers are equal, each one are different, and there should not be any central or standard theory of methodology which could fit for all the differences and which could fit for all the different rivers. Let's see, let's take the comment of Heraclitus of at least 2500 years before, that no man ever steps in the same river twice, for it is not the same river and he is not the same man. If you step inside a river now and after a few seconds you like to step into the same river second time, then by this time the river changes, and as a man you are also changed, because for the first time you don't have any experience, but while in the second time you enter into the river, you are an experienced man. So the systems are so dynamic, and these dynamic attributes are to be understood while putting any impact, any intervention into the river. So no two rivers are equal. I am giving you some example. Each river system is unique. Why unique? Because every river works on a different boundary conditions. Those boundary conditions may be the fixed boundary conditions like lithology, geology, climate, drainage area, valley settings, flow. So all these are the fixed boundary setup on which a river walks. At the same time, there are the flux boundary setup which are dynamic, which are changing time to time, like discharge, sediment load, and riparian vegetation as well as the in-channel vegetation. So vegetation, load, and the discharge are always changing, and river have to adjust with those changing conditions. So every river has to work with these either fixed or the dynamic or flux boundary conditions. So dynamicity of the river or difference in the river, uniqueness of the river starts from that, because each river has a unique boundary condition. Each river develops under a unique boundary condition. And there are sets of factors, numbers of factors. River could be considered as a system where numbers of factors are integrating together. And these different set of factors are acting on a river, and that set of factors differ from one river to other. Even the ways of interactions are also different. That's why, as an outcome, we get a different river in spite of flowing on the same region. Say, two rivers are flowing on the same region, but as their factors as well as their mode of interactions change, we are observing, we are getting a different. Okay? And this interaction and dominance of factors which changes time to time, from one season to other, from one year to other. Even the character of the river changes because of the changing in the interacting factors as well as their mode of interactions. All these are naturally dynamic. But if we set our control or intervention on this dynamic system, then the things would be more complex. So a river is not only a channel of water, is not only a channel through which water flows or sediment moves, but it's a entire area. River could be understood in their catchment and landscape context. River is not only the channel, river is the entire area of the catchment. It represents entire character of the catchment. Okay? So this could be realized if we see how a river develops. Generally, our idea is river forms at the highland and it moves downstream. But actually, river is not originated from the highland. River originates from the bottom lower section of the landscape, where the runoff is accumulated and the threshold energy is available to cut a channel. So a single channel is cut at the lowermost part of the landscape, and gradually it extends headward. So as a river extends headward and then the catchment it spreads over the entire catchment, then since the origin and during its evolution, all the characters of the catchments are imbibed, incorporated, and then imprinted on the river. So while we see the river, it doesn't represent the channel only, it represents the entire catchment through which it flows. So our understanding should be broader. We have to see a river through its catchment, not only through the channel, Okay? So no two rivers are equal. I am going to give you some examples. See, it is the road, the National Highway 17, in the duars of say North Bengal, where numbers of rivers emerge from the mountain slope, Himalayan slope. Within 10 to 15 kilometer, you will see 4 to 5 large rivers which originates on the mountain slope and emerge the Piedmont areas. So river Lees, Mal, and Chel. So these are the small rivers, and you see they are originating from the same geological setup. They have the same geological setup, and they are sharing almost same region, but they are different. You see the Lees River at first, downstream from the bridge of along National Highway 17, it is the Lees River. Now you see how the His River is. Now see the Chel River. All the rivers are flowing side by side within 4 to 5 kilometers apart, and 8 kilometers apart another river, Mal River. So they are sharing almost same geological setup and mountain front, but they are actually different. If we see the upstream, how the river looks like in the upstream of the river bridge, Lees River, His River, Chel River, and Mal River. So no two rivers are equal. Even a same river changes downstream. I have taken the Chel River for example, how it changes from source to mouth. It is the Himalayan front, and when it touches the Piedmont, the valley setting or the confinement pattern changes, and the entire character of the river changes. It is within the mountain front, and here just below this, and it is near the mountain front or the Piedmont, and this is at its slightly lower part, and it is at this estuary while it meets with the river Naura, okay, before joining the Tista River. So a single river also changes from source to mouth. So this is the classic downstream trend. As the river moves from source to mouth, its confinement pattern changes. Near its source, it is confined, and after that, it becomes partly confined, and near its lower reach, it becomes laterally unconfined. And this confinement pattern controls most of the behavior of the river. At the same time, the gradient changes, gradient reduces. Along the channel, gradient reduces downstream. Bed material size reduces, but stream discharge increases. Total stream power increases up to the confined setup, and then it starts declining. And then the stored sediment, volume of stored sediment, and time of duration of the sediment storage increases downstream. Relative volume of stored alluvium and their time of residence increases downstream. That means whatever depositional features we are observing along the river, their instability gradually reduces downstream. At the upper course, they are more unstable, and while we move downstream, they are becoming stable, more and more stable. As the grain size reduces, the cohesion increases, and that cohesion gives the stability to the deposited materials. Okay. So as the river discharge increases downstream, the fundamental character of the river, hydrological character, stream hydraulics, changes. With the increase of discharge, channel width increases. We know this. With increase of discharge, channel depth increases. Channel depth means here the flow depth. Flow depth increases. And with the increase of discharge, river velocity, water velocity increases. We have a different idea that from source to mouth, velocity of the river reduced. But actually, the research shows that from source to mouth, in spite of reducing gradient, velocity increases because the grain size reduced and the bed frictions or boundary frictions reduces. So due to the reduction of boundary friction, actually velocity or resistance to flow, this is the resistance to flow. Due to the reduction in the resistance to flow, actually velocity increases. Okay, this was proposed by Leopold and Modoc in 1953, and presently it is after the Fayers and Bayerle, it is also proved according to the recent research of USGS. Okay, so take a very simple example of Chel River, how it looks like in the upper course. You see, in the upper course, the river is flowing through the large boulders, and that's why boundary friction or the resistance to flow is maximum. That's why its velocity is quite less. While it comes down to the pigment areas, due to reduction in the bed materials, friction reduces. And while it comes to the estuary, then the bed material further reduces, and so the velocity, we measure the velocity in 3 cases, gradually from source to mouth, velocity increased. Okay? A same river also changes with time, that we have already discussed. Due to the change in the Buck's boundary condition, river discharge changes, sediment load changes, vegetation changes, riparian vegetation as well as the in-stream vegetation changes, and that's why a river changed. Okay? So the flow sediment interaction changes, flow vegetation interaction changes, flow landform interaction changes, and which leads to the ultimate change of the river. Now, question arises, while we go to the river to understand it, to study it, to make a research on it, to carry on research on it, then how to proceed? Because the river is so dynamic, so complex, and it is changing with time. So it is very difficult to study a river because it is a far complex process and landforms are constantly changing. So how should we proceed? To me, there is no standard framework that can perfectly explain every river system because every river is unique. That's why we should go for the field with a detective style of investigation. At first, we have to examine the relative importance of multiple factors. There are multiple factors are interacting at different part of the river, and we have to examine what are the dominant factors there and how those dominant factors are interacting together, how the process are developed by the interaction of those interacting factors, and how the landforms are generated out of that interactions, due to that interactions, and how those entire things are being changed from time to time. So there is a requirement for evolutionary studies or recurrent visit. Say for example, this river system or this small gully channels, gully system was studied in 2007. How was it? How does it look like? 2008, 2009, 2010, 2012, like this. So if we concentrate on a particular river system in that particular style of research, then only you will be able to have an understanding about the behavior of that particular river. And as a river is a large area, as the catchment is large enough, then we must proceed with nested hierarchical approach. What is the nested hierarchy? In a large catchment, there are numbers of smaller catchment or sub-catchment. Within a sub-catchment, there are numbers of micro-catchments. In one micro-catchment, there is further micro-catchments. So in this way, the smaller units, smaller landscape or catchment units are nested in the larger one. In this way, entire system develops. So we must understand a large river in this nested hierarchical system, and we have to start with the smallest one at first. How the smallest one or smaller landscape units are nested within the larger one. And in this way, we should proceed and we should have a detailed understanding or clear understanding of the entire catchment. For a particular river, you have to start with the smallest geomorphic unit, like cascade, waterfall, floodplain pockets, ripple, pool, bar, cutoff, backswamps, levees, etc. And how these numbers of geomorphic units are nested in different reaches. It is the upland swamp reach, it is the gorge river reach, it is the partly confined reach, it is the meandering reach. So in this way, in a single reach, how the numbers of geomorphic units are nested, and then how the numbers of reaches are nested in an entire catchment. This should be our method of research and mode of proceedings. So if we visit a particular place, say this is a place where we like to visit, and it is the Chel River, National Highway crossed this river here, and if it is the place of our field study, then at first we have to identify the geomorphic units, and then we have to understand how the process form relationships are operating there. So these are the geomorphic units: point bar, mid-channel bar, pool, refills, chute channels, floodplain, terraces, like this. And how the process form relationships are there. Okay? Say take an example of the say this one: flashy and variable discharge, huge sediment load, inefficient longitudinal sediment transfer, renewed downcutting associated to lateral irrigation. All these processes are responsible for the development of these geomorphic units. And now go to the second step. Identify and interpret the assemblies of geomorphic units at each risk scale. Within this risk scale, what are the assemblies of geomorphic units? The braided system. There is the human interventions. Okay? And then, so in this way, I don't like to proceed much, because it will say kill your time. And Madam Snehalji, how long you can tolerate me?
Sir, as long as you want to carry on with you, please go ahead. Because
Okay,
today we are all
thank you
learners,
very
we
much.
are trying to learn. Yeah.
For another 45 minutes minimum, you can carry on, sir. We are learning a lot from you.
Okay, sir. Okay. Now, in the second part of my discussion, we like to understand how this complexity is enhanced due to the human interventions at different spatial scale. Okay? Take the example of channel constriction at first. So it is the site-specific human intervention. It is the site-specific human intervention where the channel is being constricted for the construction of bridge. Okay, channel is this river, Chail River are constricted for the construction of bridge to minimize the length of the bridge. Okay. So while we enter to the river front, the river is so large, so it is very difficult to understand the impact. That's why we made one small arrangement of the experiment. We divided a river into a small part and left it for some days to get normalized, and then we made our experiment. So let's see how the experimental site is being constructed. So the large river is divided to develop a small channel, and then we understood its flow pattern and river behavior. You see, the flow is almost tranquil and laminar within our constructed reach. Okay. Now we try to constrict the channel by putting two boulders on it. This experiment could be done in the laboratory, but it will be in that case a totally artificial construct. But to know the natural system, better to make this experiment under the natural setup. Okay. So you see how the river is being changed entirely. Now the laminar flow is transferred to the turbulent. Yes. The flow pattern is entirely changed. It becomes turbulent now. And after the flow pattern is changed and river hydraulics is changed, energy distribution, energy availability also changed, and scouring starts. And the scoured materials gradually spread downstream. So we made some important measurements of velocity, depth, then critical bed shear stress, and all these are put into the shield diagram. And it is in the shield diagram, it is the erosional domain, it is the transportational domain, and it is the depositional domain. Previously, in original setup, the river was under this transportational domain, while only the sediments are being transported. But now, in the altered setup, after the constriction, the entire behavior of the river is changed and it becomes the erosional. Okay, this is how the entire river character is being changed by the constriction of the channel. So this is a site-specific impact, and for better understanding, we made this experiment. Now, in micro watershed scale intervention by the check dam constriction, this is the real basin I have shown you earlier, and we put check dams in 2008 with the locally available laterite boulders with some soil coating on it, and then system is altered in 2009. Sediment is trapped, the flow is trapped, sediment is trapped, and that trapped sediment helps the vegetation to grow, and this vegetation helps more sediment to trap. So a positive feedback system occurs. More sedimentation, more trapping of sediments, more vegetation means more trapping means more vegetation, and in this way. So entire character of the region has been changed. Okay, and we made some important measurement according to it in this line. So it seemed that the erosion is checked here. Yes, of course, where the check dams are put, so it is the former check dam. This is the former check dam. This is the former check dam, and so sediment is there and erosion is checked. But if we look it from the other side, so these are the check dam sites, and these check dams restricted erosion and enhanced deposition in the lower part, but erosion is enhanced in the upper part. Why? Because the base level has been shifted. It was the base level of the river. Now the base level has been shifted. Effective length of the river has been reduced, but height was not reduced so much. It was the previous gradient, and now it is the gradient. So gradient is now steeper at the upper catchment, and which helps in the further erosion or more erosion in its source region. So putting or intervention at one side may lead to the impact on the other side. This is called offside response. Okay, offside response of human interventions. You are intervening at one part, but the impact is there on the other part. This is how the impact of large dams are also maybe there in the upper catchment of the channel. It is the original long profile, and now if you put the check dam, base level has been shifted, and there is the deposition now. Now the river has to make more erosion to get equilibrium condition, or to make a graded slope at its upper part. Okay, because this original gradient is now steeper for this section of the river as the distance reduces. Distance is reduced, but height is almost same. That's why gradient becomes steeper now. So these are the offside response that we are expecting or we can expect. But similar check dam may set another response to another site. Let's take another small example. Say it is a gully basin in Paschim Medinipur district of at Gorbeta in Paschim Medinipur district of West Bengal, and in this gully basin, 2 check dams were constructed at its mouth, and these are how those check dams are working. And at the same time, gully plugs were also constructed. These are the gully plugs. Gully plugs were constructed along the gullies, and that's gully plugs. Those gully plugs help the sediment to trap along the channel, and the channel bed is now filled up. There is no down cutting now, but there starts so valley floor is armored, or valley floor is filled up, clogged with the sediments, and as there is no down cutting, lateral erosion starts. Okay, so in one case with putting of check dams, headward erosion started or increased, and in other cases the valley side erosion started. So all these are very local impacting rather, and we could be more serious about it, or if we give the attention to this affected locality, then the problem could be addressed. So varied response to similar intervention, almost similar intervention may give the varied response. There are lagged response. Sometimes you get the immediate response, sometimes the response are lagged. So it depends on the system sensitivity, how sensitive your system is. If it is more sensitive, then immediately you can get your impact. But if it is not so sensitive, then the impact will start after some time. So there would be accordingly there would be the variation in recovery time also. So it makes the river system further diverse and unpredictable. If we come to the reach-scale intervention, let's take one example of Damodar River basin. You know, this is the Damodar River, and earlier there were numbers of distributary channels. Actually, it was a delta fan. Okay. These were the earlier distributary channels, and Damodar River is famous for its flood. And previously, these flood water used to get distributed along those distributary channels. These are the flood areas. But during British period, the British government put embankment on both sides of the river Damodar in 1856. But immediately they realized that these two embankments are within this narrow stretch or narrow confined channel, these huge water could not be accommodated. That's why they removed the right-hand embankment. But left-hand embankment remained as usual. And it dissociates the earlier distributary channels, Kunti, Kana Damodar, Kunti, Behula, etc. Okay, so all these distributary channels are getting dissociated and isolated from the main river. So as a result, what happened? This was the earlier channel, active channel in 16th, 17th century. In 18th century, these became the active channel, and now it becomes the active channel. All these rivers are excluded from the main river. Okay. Now, as the flood concentrates here in this present channel, then numbers of options are there. Several times people are asking that whether these earlier channels could be recovered or could be connected to the main river now or not. Then one of our study shows that as these channels were isolated or excluded for long time, the main river channel is now far lower than the distributary channels. So there must be a large flood of 5 to 10 years recurrence interval to reach the water to these distributary channels. Okay, so Damodar River is now at lower from the Kana Nodi. Damodar River is now at far lower than the Gangu River. It may be possible by dredging, partial dredging, as well as by say accommodate or to moderate the large magnitude flood. Okay, so these are part of our suggestions. Now, if we go for the catchment scale intervention, in the large scale intervention, take the example of Indian Sundarban. You know, in Indian part of Sundarban, there are 102 islands, 54 were reclaimed with an area of more than 5,300 square kilometers with the help of 3,500 kilometer embankments. So mechanism was very simple, putting embankment on either side of the channel and clearing the forest. Okay. So under natural setup, while the river was connected with its intertidal area, then during the high tide, as the high tide proceeds, then the flood deluged or flood water spreads into the islands, into the deep forest. Then water cannot proceed much because these plants offer the shearing resistance. Due to the high level of shearing resistance, the flood water cannot proceed much, or its velocity was retarded. That's why the velocity of the high tide was less. than the velocity of low tide, because low tide water moves according to the gradient, according to the gradient and gravity. So low tide was stronger than the high tide. All the sediment and water which pushed inside during high tide was easily cleared during the low tide. That's why all the channels were hydrologically fit and geomorphologically competent and free from sediment. But as you put in embankment on both sides of the river, the channel is restricted within the embankment. It cannot flood the islands. And as there is no shearing resistance, then velocity of the high tide is increased. At the same time, the depth of the water also increased. As the depth of the water is more, and due to the absence of shearing resistance, velocity of the high tide is high enough. Now the high tide becomes stronger than the low tide. So entire system has been altered. Previously it was a ebb dominated system. Ebb tide was dominating. It was a ebb dominating system, and now it becomes the flood dominating system. Okay? So during this flood, as the energy is high, huge amount of sediments are pushed inside, but the sluggish and slower low tide cannot drain all those sediments downstream, and it leads to the sedimentation within the channel. So you see how the channel is hydrologically fit and geomorphologically fit under a dominating system, and you see how the channel is getting gradually sedimented in tide dominating system. So entire estuarine system has been toppled, has been changed. So as a result, what happened? There is in-channel sedimentation and drainage decay. There was a channel in 1920, 21, 1930, but in 1960, channel is absent. What was the fate of the channels? Yes, you see, as there is gradual sedimentation within the channel becomes narrower and filled with sediment and gradually occupied by the man. A large river is transferred into series of fish ponds or fisheries. So this is how the huge number of internal drainage system, almost all the internal drainage system is occupied by human being. And thus the water holding capacity of the entire interior part of the Sundarban Delta has been lost. If we see, if we divide the entire reclaimed part into numbers of subcatchments, you see all these small channels, the lighter blue channels, were now excluded from the main river and occupied by human beings. All these are the subcatchments. All these are the subcatchment-wise maps, and these are mapped and surveyed. And see, it was the previous one, and now tidal spill channel and tidal spill areas, and all these spill areas now are excluded by the construction of embankment. At the same time, all these small channels are now decayed. So as a result, spill area is reduced almost by 100% in all the estuarine system or subsystems. And more than 2926 million cubic meter water holding capacity is lost. So what happens during the storm surge, during spring tide? You see, the water concentrates along the main channel only. There is no scope for the distribution of the water, or water holding capacity is only restricted to the main channel now. And water level moves up, and this is how the islands are situated and where the river is situated. Islands are much lower than the river. People are trying their best to elevate the height of